Okay, so let's start.
Yes.
So again, welcome everybody to this NewAthena webinar in the series. Today it's a pleasure for me to present you Alessio Marino, who did his PhD with a joint program between Palermo and Toulouse in 2021. He then moved to Barcelona to the, I never know the name, the Institute of Space Science in Barcelona, and he has been there since. He's also an associated, is a member of the Einstein Probe, and is in other international collaborations such as Theseus, good luck there, and EXTP. And his research covers multi-wavelength observations of both low and high X-ray, high mass X-ray binaries and isolated neutron stars. And today he's going to tell us about dense matter in equation states in isolated neutron stars. Now the floor is yours. So you share the screen.
Yes, thanks a lot for the nice introduction. I'm sharing the screen. Can you hear me, right?
Yes, I can hear you. I can see
And you
you
can
in
see my screen.
the full
and...
screen. Yes.
Oh, okay, perfect.
Excellent.
Let me just put maybe this here. Okay. So, hi everyone, thanks for the introduction and thanks for inviting me to give this webinar today. I am actually very excited to share these results with you. This is a work that was published last year on Nature Astronomy, and that, as you can see, it has 4 corresponding authors. It kind of reflects how multifaceted this work was. It involved observations, simulations, machine learning. So it really needed a substantial and exceptional team effort. So I have to start by thanking my comrades in this very nice project. Okay. So the focus of this project and this talk is to show you how 3 very young and yet very cold neutron stars allowed us to put some constraints on the dense matter equation of state and therefore taught us something very fundamental about all neutron stars. So I will start from, let's say, being very basic about neutron stars. Probably this is not necessary, but just to be sure that everybody is on the same page. When we talk about neutron star, we are talking about the end point of the life of very massive stars. And what we typically say is that a neutron star is what you get when you squeeze a star, which is like the sun or maybe slightly more massive than the sun, within the size of a city like Barcelona or Amsterdam, a radius of 10, 12 kilometers, which means that these objects are extremely dense. And because of that, we can consider neutron stars as the perfect laboratories to study matter in the context of extreme gravity, extreme density, and extreme magnetism. Indeed, neutron stars are the strongest magnets known in our universe. We know plenty of neutron stars. We expect in our galaxy alone to have 10 to the 8 neutron stars. We actually see only the tip of the iceberg of the whole populations. Indeed, the number of neutron stars that we know and that we have observed is slightly less than 10 to the 4. And this population of neutron stars is very diverse. We have pulsars in binaries, we have neutron stars, high mass and low mass X-ray binaries, we have magnetars, CCOs, a lot of acronyms. But the most common beasts that you can encounter in terms of neutron stars in our galaxy is composed of radio pulsars. Actually, the very first neutron star ever discovered, ever identified, actually not discovered, was a radio pulsar. It was discovered by Dr. Jocelyn Bell-Burnell in 1967. These radio pulsars are mid-to-late neutron star where the emission comes from a synchrotron beam. And whenever this synchrotron beam of radiation intercepts our line of sight, we see a pulse, we see a peak in the radio emission. And therefore, we can then measure the interval between peaks to measure the spin period of the neutron star, because these peaks are clocked at the rotation of the neutron star itself. Now, we call them radio pulsars, but actually we see pulsations across the whole electromagnetic spectrum, from radio to X-rays and gamma rays. And these pulsars can be kind of approximated as magnetic dipoles. Indeed, if we measure the spin period and the spin period derivative, these are the most typical observables that we can have from these neutron stars. We can use the dipole approximation to have an idea of the magnetic field of the neutron star and of its characteristic age. However, both these values have to be taken with caution. the magnetic field, first of all, because we know that the magnetic field from these neutron stars is probably more complex than just a dipole. So considering it a dipole is really just an approximation. And secondly, for the characteristic age, this value is based on the assumption that the magnetic field doesn't change over time. This is a strong assumption. We know that actually the magnetic field tends to decay since the birth of a neutron star, but we can still consider this characteristic age as an upper limit on the real age of this neutron star. This is something that will come back in this talk. Okay, so we can then use the P and P dot that we observe from these neutron stars to have a clear visualization of the whole population of neutron stars in our galaxy. What as neutron stars people typically do is to indeed plot our neutron stars in a PP dot diagram, where we can also plot some horizontal lines, some isomagnetism lines that identify also different magnetic fields of the neutron stars in our galaxy. And as you can see, the population of known neutron stars is clearly divided in two main families. There is this big bulk of neutron stars at relatively high spin periods and high spin period derivatives and magnetic fields. This is the population of young to middle-aged neutron stars. And then we have in the bottom left corner of this diagram a population of neutron stars which are very fastly spinning with periods of about millisecond, but also have very low magnetic fields and spin period derivatives. This is the population of millisecond pulsars. And it's no coincidence that they coincide with the population of pulsars in binaries. Indeed, their very fast rotation is due to an exchange of angular momentum between these neutron stars and a companion stars in a binary. This is how they can attain such high spin frequencies and yet have such low magnetic fields, basically. Now, the focus of this talk are actually this population of neutron stars. So let's take a look at them in particular. These are all isolated neutron stars. In this talk, the different colors are coded for the different magnetic fields. From blue to red, we have low to high magnetic fields. And the labels are for neutron stars that we observed in the X-rays. Now, we distinguish four main classes in the PP dot diagram of isolated neutron stars. We have, again, rotation-powered pulsars, powered by rotation, emitting typically in radio, but actually we also observe them sometimes in X-rays and gamma rays. We then have a population of central compact objects. They are here in the bottom. They are young, actually. They are still associated with their supernova remnant. Actually, they're at the very center of the supernova remnant. That's why they're called like that. They typically emit in X-rays, and they emit purely thermal spectra. We don't really see pulsations from these objects, with a couple of exceptions, and they have very low magnetic fields. This is kind of a mystery on its own. Indeed, they are sometimes called failed magnetars or anti-magnetars. We then have, going a little bit to the top of this plot, a population of so-called X-DINs. They are relatively high magnetic field neutron stars, still powered by their magnetic energy, but they emit pure black body spectra. They mainly emit in X-rays, and they're all in our neighborhood with distances below 1 kiloparsecs. And they're thought to be the descendants of magnetars, which are the last class I'm going to talk about. Magnetars are, well, the main characteristic of magnetars, as the name suggests, is their incredibly high magnetic fields. They have magnetic fields of order 10 to the 14, 10 to the 15 Gauss, which is justified by the fact that they are very young neutron stars. And this high magnetic field is the reason why we have a very rich phenomenology from these sources. We have outbursts, we have bursts, we have giant flares, and so on. Now, there is therefore a clear observational diversity in the neutron star family, and yet we think that all neutron stars inside more or less look the same. Let's take a journey to the center of a neutron star. We can imagine a neutron star as like a big onion made of different layers. We go from outside in, we have an ocean or envelope of low density. Then we have at increasing density an outer and the inner crust. where matter becomes more and more amorphously organized. We start from a lattice of nuclei to then go to a more condensed nuclear pasta phase. And finally, after just 1 kilometer, we get to the core of the neutron star. Now, the core of the neutron star is a regime of mystery, in the sense that we don't really understand and we don't really know what the core is made of. Is it made of neutrons? Is it made of nucleons in general, of kaons, hyperons, whatever? And also, we don't know how this matter behaves in this regime. Such a regime is called ultradensity. We might know the composition and the behavior of matter in this regime if we know the equation of state, which is typically considered a relation between the pressure and the density of matter, but it can be expressed in the case of neutron star as a relationship between the mass and the radius of neutron stars. But unfortunately, we don't really know which is the correct equation of state. We have plenty of options. Nuclear and theoretical physicists have developed dozens and dozens of possible curves, all of them connected to a different specific chemical composition of the neutron star core, but we don't really know which one is the correct one. And as you can see, one way to find it would be to have precise measurement of the mass and the radius, but they have to be very precise, because as you can see, we have plenty of equations of state all condensed within a very small range of masses and radii. Anyway, we still, want to find the equation of state, even though it seems very hard to do. It's actually one of the holy grails, I would say, of modern astrophysics. And I say astrophysics because we cannot reproduce such a regime in an Earth laboratory. So the only way to constrain the equation of state is to look at the sky and try to find constraints from astrophysical observations. The astrophysical community has indeed come out with many different techniques to find the equation of state from astrophysical observations. Here you have a catalog of possible methods. They can allow you to find the mass, the radius, the compactness, and then from them have some info on the equation of state. I will not, of course, go into details of all of these methods. I will just focus on the method that we used in this paper, in this work, which is cooling. Now, what is the meaning of cooling? All neutron stars are born hot, but then they will cool down over time. This is, let's say, the basic statement that we have to do. But the thing is that the way they cool down depends critically on their mass and their equation of state, their chemical composition. Let's see a little bit how. Here is a typical cooling curve of a neutron star. This is a simulated one for a 1.5 solar mass, and an equation of state which is called BSK24, which is just a nucleonic equation of state with a high proton fraction in the core. So neutrons and protons. As you can see, we have this cooling curve here. And this cooling curve is the result of two competing processes which make this neutron star cool down over time, which are the neutrino cooling and the photon cooling processes. So the neutrino cooling is just an ensemble of processes like direct Urca that fundamentally release neutrinos. Sorry. These neutrinos will take away energy from the neutron stars because neutron stars are mostly transparent to neutrinos, so they can escape the neutron star, taking away a fraction of the energy of the neutron star. While the photon cooling is just these neutron stars will release radiation, and this radiation will also take away energy from the neutron star itself. Now, the neutrino cooling is much dependent on the temperature of the neutron star, because you need to have very hot cores in order to activate these neutrino releasing processes. Therefore, neutrino cooling dominates until the neutron star is about 10 to the 5 years old. This is called the neutrino cooling era, while the photon cooling era dominates afterwards. Now, there is an issue here, and the issue is that the neutrino cooling is dependent on the temperature, but therefore is also dependent on the mass and the equation of state of the neutron star. The equation of state, because you need to have enough protons, for example, to activate some processes. So not all chemical compositions will activate some neutrino processes. And the mass is also important, because the higher the mass, the higher the temperature in the core. Just to show you this, instead of just saying that, if I do the simulation for a 1.9 solar mass neutron stars, even though I'm just slightly increasing the mass of my neutron star, my cooling curve proceeds in a much different way. Now we are cooling down in a much faster fashion with respect to the 1.5 solar mass neutron star. Actually, we call these two ways of cooling as a minimal or standard cooling and then enhanced cooling. Now, two takeaway messages. The enhanced cooling can be activated only by some equations of state. Not all equations of state will get to the point to have such a fast cooling in the first 100,000 years of life of a neutron star. And the second thing is that even for some equations of state, enhanced cooling is only activated for typically massive neutron stars. So the point here is that if we find a neutron star or several neutron stars that are very young and yet very cold, it means that they have had to have experienced enhanced cooling. And this is a way to constrain the equation of state, because only some equations of state can allow the existence of these young and cold neutron stars. And actually, this is not a new idea. There have been several claims of enhanced cooling in the past for both isolated and accreting neutron stars. The problem is that there has never been a smoking gun evidence for cooling, for enhanced cooling, because for isolated neutron stars, there is model dependency. There is the issue of the age and the distance of these neutron stars, which are typically not very well constrained. I told you before, if we use the characteristic age, for example, this cannot be considered a reliable estimate of the age of our neutron star. Is actually just an upper limit on their age. While for accreting neutron stars, there is always the issue that we cannot be 100% sure that the emission that we see from these systems is not coming from residual accretion instead of the surface of the neutron star. So because of all of these biases, we wanted to do a reboot of this technique, starting from scratch and basically analyzing all the observations that we could find in the archive, but using this time up-to-date ages and distances for all of these neutron stars. Then we ran magneto-thermal simulations to simulate the cooling histories of this neutron star, and finally compared theory and observations by means of machine learning and astrostatistical techniques. My role in all of this was mainly focused on the observational part, so I will talk at length about this part. So we've had a sample of 70 sources, all of the known isolated neutron stars emitting in X-rays. So we used only data from XMM-Newton and Chandra because we want the best data for our sources. Also, most of them are pretty faint, so we actually need very sensitive X-rays instruments. And we analyzed all these spectra. Now, the typical spectrum of an isolated neutron star is composed of two components. Sorry for the repetition. We have a thermal component coming from the neutron star surface. This is what we are interested in. And then sometimes a non-thermal component, which can either come from the pulsar magnetosphere, or it can just be the result of contamination from the surrounding nebula. Now, we don't actually care in this moment about the non-thermal component. We just want to focus on the thermal component. So in the following step, we have excluded the power law component and just focused on the thermal one. We have modeled this component with not just a black body, but also neutron star atmosphere models, which are a little bit more sophisticated. Having different models to estimate the flux allowed us to check that our results are not model dependent. And then from the flux, we just have to use the distance to go to the luminosity, which is our final goal. And of course, we need the age because we want to have a luminosity versus age diagram ultimately. Now, this is a crucial part because, again, we in principle have age and distances for all radio pulsars because the age is based on the characteristic age, while the distance can be estimated from the dispersion measure of our pulsars. However, neither of these methods to find the age and the distance are very reliable. So in this work, there will be a forthcoming paper that includes the whole sample, but in this work in particular, we just focused on sources that have a real age determination and a well-measured distance values. So what does it mean, real age? A real age for a neutron star, it means that either we have an historical record of the supernova that birthed these neutron stars. So we really have the birth date of these neutron stars, or we know the associated supernova remnant to these neutron stars. And supernova remnants actually offer many ways to constrain both the age, but also the distance of neutron of the supernova remnant, and of course of the neutron star. Which actually means that neutron stars with an associated supernova remnant are the perfect candidates for this work. The other way in which we have a nice and well-estimated distances for these sources are proper motion. So applying this filter, which is only sources for which we have a real age and a well-determined distances, forced us to go from a sample of 70 sources to a sample of only 15 sources, so reducing sensibly our sample. So this was the luminosity versus age of all the sources that we have analyzed at the beginning. And then this is the final sample with only the sources for which we are sure about age and distances. Now, this is the final sample. If you see some white points here, it just means that we don't have any estimate for the magnetic field of these sources. Indeed, these are CCOs. And as I told you, CCOs are not pulsating, so we don't really see the period and the period derivative of these sources. So taking a look at this final sample, it immediately catches the eye that three sources here are kind of standing out with respect to the rest of the sources. They are very young, with ages below 10 kiloyears, but also very cold. They are colder than their companion pulsars and neutron stars. So these three young and cold neutron stars are the focus of the rest of this talk. Let's meet them. They are two pulsars and one CCO, the one associated to Vela Jr. They're young, they are close by relatively, 2-3 kiloparsec, maybe less. So they're all in our neighborhood if you want. And let's take a look at their spectra. Two of them, so the pulsar and the CCO, have purely thermal spectra, while this pulsar, 0205, is actually dominated by a power law. This power law is due to the nebula which surrounds this neutron star. Now, this contribution is not what we're interested in. We are just interested in this black body component, which is there. It is statistically significant, even though it is, of course, not the dominant spectral component in this spectral emission. But we just took into account this component in the rest of this work. Now, these black body components are relatively cold. They have temperatures of 100, 300 electron volts. And also the size of the regions emitting this thermal emission is relatively low, is relatively small. We are talking about sizes of a few kilometers, even less, for example, in the case of the CCO. So it means that we are not watching the whole emission from the neutron star surface, but we are just watching the contribution from a hotspot on top of the neutron star surface. And this begs the question, are we missing a piece of the overall emission from these neutron stars? Which means like we are expecting the whole neutron star surface to emit some radiation. Is it that these sources are so cold just because we are not seeing a part of the emission coming from the whole surface, which is colder but still there? And this is possible because, of course, in between us and these neutron stars, we have interstellar medium, which absorbs the part of the X-ray emission, and it might be responsible for hiding away this extra component from the whole neutron star surface. So in order to test this scenario, we have added in our fits an additional black body component of radius fixed to 11 kilometers. This is not important. It could be more, it could be slightly less. It doesn't really depend on the radius that we choose for our black body. But then we left the temperature free. So leaving the temperature free and launching the fit, we have an upper limit of this possible extra component of the neutron star surface emission. And we have included the luminosity associated to this extra component in our observational data. So we are really putting ourselves in the worst case scenario. We're even including luminosity that might not even be there, actually, because again, we don't have any statistical need to include this extra black body component. Okay, so this is about the observations. Let's take a look at the simulation part. We are using MATINS, which is a 2D code that takes into account several parameters. The most important ones are the magnetic field, the mass, the equation of state, and the envelope chemical composition. Now, in this work, we are playing with 9 values for the magnetic field, going from 10 to the 12 to 7, 10 to the 13 Gauss. If you think that this range might be a little bit low, considering that this neutron star can even get to 10 to the 15 Gauss, the reason why we focused on low magnetic fields is that, well, first of all, these neutrons, we have estimates of the magnetic fields of these neutron stars, and they are in this range. So, okay, it seems to be justified. But also, even more importantly, if we consider higher magnetic fields, we would have these neutron stars hotter, not colder. And in this case, we just want to focus on how to explain why these neutron stars are so cold. So that's why we are just isolating a range of low magnetic fields. We then have 3 values of the mass, 3 equations of state. If you are not familiar with these codes, I am not, for example, just think of slide 4 as being a nucleonic equation of state. BSK24 is also a nucleonic equation of state, but in this case, we have a higher proton fraction. And finally, GM1A is a more exotic, is a hyperonic equation of state. And finally, for the envelope, we have 2 flavors, light, so it means hydrogen and helium, and heavy, which means mostly iron. In this case, we are also focusing only on the heavy case because a lighter envelope would make, again, our neutron stars hotter. And we really want to focus on putting ourselves in the worst case scenario to see how to make these neutron stars extremely cold. So we end up playing with all of these parameters with 81 possible cooling histories for each neutron stars. We can see them in these panels, each of them for a different equations of state. Now you can see there is a jungle in each panel of curves. The colors are coded again for the magnetic fields. The lighter the color, the lower the magnetic field, as you can see here in this color bar, while the style of the lines are connected to the mass of our neutron stars. 1.8 solar masses, so the heaviest neutron stars are marked with solid lines, while with dashed and dotted, we highlight the curves for lower mass neutron stars. Now, if we take a look at these curves, there is one thing that immediately jumps in the eye, and the clear difference between 2 equations of state and the first one. Slide 4 doesn't populate this region, which corresponds to low thermal luminosity and also low age, while this region is well populated by the other 2 equations of state. As you can see, for example, in this case, the curves that actually populate this region are solid curves. So it means that they are populating this region if we allow for a heavy neutron star, for a high mass neutron stars. Let's say surprising. So in other words, 2 equations of state are activating enhanced cooling, while 1 equation of state is only activating standard cooling. And again, this is because for these 2 equations of state, we can trigger processes like direct Urka, which makes our neutron star cool down much, much faster. Now, what happens when we put observations and simulations together? As you can see, we have that while the rest of the population can be described by all 3 types of curves, the 3 neutron stars that we have isolated at the beginning of this talk can only be described with the blue and green curves and cannot be compatible with any of the slide 4 equation of state. So let's say the mere existence of these 3 young and cold neutron stars discards slide 4 as the equation of state. So if you want, this result is already kind of strong by eye, but we wanted to go a little bit further on and just quantify how unlikely it is that slide 4 is actually compatible with these young and cold neutron stars. So we invoked machine learning. And basically, we use the fact that we can run our simulations also not only in a luminosity versus age space, but also in a pp dot space, in a pp dot diagram. Here are the simulation in our pp dot diagram, and here you have our two of the 3 sources that we have in our sample. Now, this is important. We can do these tests only for the pulsars. we have to take out the central compact object just because we don't have P and P dot for that source. Anyway, so what we do is we consider these neutron stars in a 4-dimensional space made of P dot, luminosity, and age. And we consider the proximity between these neutron stars and each of these curves as the probability that these neutron stars are actually described by that curve. And we visualized all of these probabilities together in this pie chart, which I like to call like a trivial pursuit plot, because if you have ever played Trivial Pursuit, they kind of looks like the pie pieces of Trivial Pursuit. So anyway, in these plots, each of these pieces of these triangles is connected to a specific simulation, and they are organized in magnetic field, mass, and then equation of state, which is just the whole big sector made of the 3 subsectors for each mass. Now we superimpose to each of these cloves an histogram, and this histogram is the height of this histogram is connected to the probability of that specific simulation. So for example, in this case, we have the simulation at 10 to the 13 Gauss, 1.8 solar mass, and the equation of state BSK24 has a probability of about 20%, slightly less than 20%. Then we can sum all of these single marginal probability to have the cumulative probability for each of these equations of state. I'm not going to the detail, just to say that slide 4 for both sources have a probability which is about 5 or 4%. So it means that we can say that the probability that these neutron stars are actually compatible with slide 4 is very low, is lower than 5%, which is a pretty confident way to exclude this equation of state. I will go back to how important this is in a minute. I just want to show you, since this is a NewAthena webinar, how NewAthena will help us in the future to do this kind of studies. In general, NewAthena will be instrumental in the quest to find the equation of state, not just for this method, but for example, for measuring the mass and the radius in quiescent low mass X-ray binaries, or in low mass X-ray binaries undergoing a type 1 X-ray burst, measuring the inner disk radius around the neutron star and finding constraints, therefore, on the radius of the neutron star. So there are several ways in which NewAthena will allow us to find constraints on the equation of state, but also what NewAthena will be able to is to allow us to find very extreme neutron stars. Let's take a look, for example, on what Wi-Fi on board NewAthena would do. Sorry, I have to move this one here. Okay. For PSRB-234, which was one of the sources that I showed you, the faintest neutron, the faintest pulsar. Now, in our work, we have included an XMM-Newton observation, which was 27 kilosecond exposures and just accumulated about 300 counts. Not enough even to use the chi-squared as statistics. While for the same exposure in Wi-Fi on board NewAthena, we will be able to accumulate 10 times more counts and have a very accurate estimates of the norm and the temperature of this black body emission. We can get even more, of course. Let's imagine to reduce the normalization of this black body first by a factor 10. We can get good constraint on temperatures and normalization with just 75 kilosecond exposure, or for a factor 50, we can get to, again, a good constraint with 100 kilosecond exposure. And reducing normalization by a factor 50 means either to shrinking the hotspot size of a factor 7, or putting our sources 7 times further away from us. So really unlocking a new population of neutron stars which are just a little bit more far away from us than the ones that we know. We can also find neutron stars which are not only, let's say, farther away or just have smaller hotspot, but are also colder. With 200 kiloseconds, for example, we can find a neutron star. We can constrain the black body, a thermal emission from a neutron star, which has a 60% of both the temperature and the normalization of PSRB-234. But also we can, for example, constrain and find thermal emission in sources like O2, O5, which was one of the pulsars again, the one where the emission was dominated by the nebula contribution, we can find in a source like this the significant emission from the black body, even if it was 10 times fainter than the case of PSR 0205. So, for example, there are many young pulsars for which we could not find any significant emission from their surface, which now with NewAthena might be good candidates to search for cold, extremely cold, and extremely rapidly cooled down thermal emissions due to enhanced cooling. And if 350 kiloseconds might seem a lot, it's true, it's a lot. Just consider that these sources are stable, are constant over time, so we can even split this very long observation in several visits to make the scheduling of this observation, if you want, easier to do. So I finish here. To conclude, we have found a pretty strong, pretty solid evidence of enhanced cooling. Actually, we are calling this the first direct measurement of enhanced cooling. We have these 3 neutron stars whose location in the luminosity versus age diagram is very well constrained, again, because we have strong age and distances estimates. And we are putting ourselves, if you want, in like significantly in the worst case scenario with luminosity and the modelization. If you think that just ruling out one equation of state is a little bit, let's say, not good, I agree, but just consider that there are several works that, for example, predicted only 20% of the commonly used equations of state activate enhanced cooling. So these results can be extrapolated and tell us that probably 3/4 of the available equations of state right now are not compatible with the mere existence of these 3 neutron stars. So that makes this result, I would say, definitely more interesting. And finally, the NewAthena era will allow us to find if existing even colder and more extreme neutron stars. So thanks a lot.
Thank you, Alessio. Very interesting, especially for an AGM astronomer. This is, this is real physics. So that's very nice. So do we have any questions? Let me see. I don't see any panelists. There is one hand raised, Kathy Romer. Kathy, let me open your microphone. Should be open now. You can talk now, you wish.
Oh, hi, Alessio. I really enjoyed your talk. People on the call probably know that I'm an X-ray cluster astronomer, so you'd be surprised how much I enjoyed your talk. But one of the side projects I've been doing for many years is looking for more examples of the X-ray dim isolated neutron stars. And we have got some nice examples of those. Now, are those still worthwhile studying, or are these particular type of sources that you're looking at more useful for the equation of state?
That's a very great question. First of all, thanks a lot for your nice introduction. Absolutely, that's super interesting. Although there is a different, let's say, kind of physics that happens in those sources. They are much older than these neutron stars. So maybe I can go back, well, a lot, just to, okay. So this was the my slide. So the X-teens, I think they have ages higher than 10 to the 6 years, so they're pretty old. When they're so old, we are not in the neutrino cooling era, but we are in the photon cooling era. So it means that we cannot really appreciate if these sources have experienced enhanced cooling or not. This is one thing. The other thing is that X-teens have higher magnetic fields than the sources that I've been working on. And higher magnetic fields means that these sources, instead of actually experiencing cooling, they're experiencing heating. So yes, they're very interesting to study the physics of neutron star, but I would say a different kind of physics with respect to what I have explored in this work. But they will be actually part of the following paper that we are preparing in our group, so stay tuned. But thanks a lot.
Thank you very much.
Okay, thank you. Any more questions? I do have a question slash curiosity. Maybe I missed it because I was taking notes. Did you mention what? I mean, did you mention XIFU?
No, I
contribution
didn't.
of XIFU?
So I didn't because I think so. I mean, I did the simulations with Wi-Fi just because I think spectral resolution is not really necessary for these types of spectral studies because we are not really hunting for lines. We're just hunting for having more counts, more photons. So I didn't really explore the XIFU. And I haven't thought about what XIFU can do for us in this sense, to be honest. But I'm very happy to hear suggestions if possible.
Because I guess you're looking for just I was going to say boring black body, right?
Yeah, yes,
Or
boring
it's just
black
a
bodies,
continuum.
Absolutely, yes, only continuum.
So,
there are some other, I mean, of course, for other techniques to constrain the equation of state, I'm thinking, for example, of looking for lines during type 1 X-ray burst, which might be gravitationally redshifted and then be connected to the compactness of the neutron stars. For that, for example, I think XIFU would be much, much more interesting than Wi-Fi. But for this specific method, I think we are very happy with Wi-Fi.
okay. Thank you. Okay, if nobody raises their hand, I still have another curiosity. At the end, you said that WFI would allow you to go to colder or more extreme neutron stars. I missed, are they are they more interesting than the ones you have? Are they more capable of killing equation of state?
So yeah, I would say, for example, sorry, I have to go again on the other side of that. Yeah, I mean, even just here probably. So let's say, for example, I find a neutron star which has a thermal luminosity. It's here, for example. I mean, maybe let's put the observation just to put it in context. I find a neutron star which is here, for example. So it's even fainter than the ones that I found. Now, in order to explain them, I have to. I mean, even these equations of state would not be enough for this neutron star because the cooling is not enough to get to these very faint neutron stars. I'm not saying that they exist, maybe they don't exist, but I'm saying that in principle, finding more, but it's right now with our instrumentation, we could not find them. So maybe this is also let's say, limitation of our instrumentation so far. So maybe if we have now instrumentation to find them, we can even put more constraints on the equation of state. Does it make sense?
Yeah. So unless theoreticians can make equation of state faster, you can kill them. It's going to be a very interesting time.
Yeah.
Okay, if there are no more questions, which I don't see any. Okay, so you have been kept in time, and I think we can
Thank you. Thanks a lot.
Close the session now. So thank you very much. And let me, Maite, correct me if I'm wrong. I think this is the last webinar of this series.
Period, yeah, the last webinar before summer. So we will come back after summer with 3 new exciting webinars that we will announce on time.
Okay, thank you. And now thank you to everybody attending, and see you next webinar after summer.
Thanks a lot.
Bye.
Bye. Thank you.
Bye.